we were talking about driver analysis. So we already talked about if you have a continuous variable X. As I told you, usually in some of the assignments nowadays, when you are attending a job interview, they're already giving you a data set where X1, X2, and so on, Xk, and the target variable Y is given to you. And then they ask you to present some insights. In these insights, you may have to present some basic reports, find some hidden patterns, and then quantify the relations. Afterwards, you may have to do some advanced analysis. We are talking about advanced analysis anyway. The machine learning models given X and Y, building a random forest model, building a what do you call a logistic regression model, decision tree model, that you will be able to manage. Okay. But what we are discussing here is how do you find these hidden insights, hidden patterns inside this data set, or the relationship between these variables. How do you find that is the question. So to answer that question, so what we have done is, if the variable is continuous, X variable, Y variable is also continuous, something like age variable, or something like income variable, something like sales variable, something like loss percentage variable. Continuous versus continuous, you have to draw scatter plots for visualization. And then when it comes to quantification of the relation, how closely they are associated with, what is the measure that we have to use? We have to use correlation coefficient. If the X variable is continuous, something like age and income, if the target variable Y is categorical 0, 1, 0, 1, buying or not buying, then you can draw some charts like histogram overlay or the box plot. Two box plots you can draw. Okay, this is continuous versus continuous. This is continuous versus categorical if you want to find the relationship between age and buying or not buying. Okay, now if you draw the box plot, when people are buying, people are not buying, this is the box plot for people who are not buying. This is the box plot for age of the people who are buying. If you see almost same box plots or same violin plots, then you would say that, our histogram overlay also, the peak is occurring at the same point, then you will say that there is not much of dependency because age is almost same, doesn't matter. Whereas if you draw the box plot, if you see a huge difference, utilization versus delinquency. Utilization, when the people are delinquent, for bad customers, or non-delinquent, this is for good customers, utilization is mostly here. For bad customers, utilization is mostly here. The median value is almost 15%. The median value in this class is almost 60%. Obviously, there is a huge difference. Definitely, utilization does matter. Utilization, if the utilization is low, you can say good customer. Utilization is high, you can say bad customer. So that's how you can show them visually that utilization and target are related. This is a strong driver. Strong driver means what? It will be having a good predictive power. Now, how do you quantify it? Do you remember the measure? How do you quantify the relationship? We have introduced a new measure there. Earlier, continuous versus continuous, it was correlation. Now it is continuous versus categorical. We have introduced something called weight of evidence or information value. If we have two variables, income and age, if you see income, as income is increasing, if you see the people, number of people who bought, number of people who did not buy, there is a clear trend that it shows people who are buying are increasing with income, people who are not buying are decreasing with income. Whereas as age is increasing, people who purchased, who did not purchase, almost same. So you can quantify this using a formula called information value. Information value is very high for income variable because, as we can see, the percentage of people who have purchased are increasing, percentage of people who are not purchased are decreasing. That's why the difference is high. Information value will be high. Whereas for age variable, as age is increasing, percentage of people who bought did not increase, percentage of people who did not buy almost same. That is why information value for age is very, very less. So based on the information value, if the information value is more than 0.1, or if it is better than 0.3, strong relationship, that variable must be included in model building. It will give you good predictive power. Otherwise, if the information value is less than 0.01 or less than 0.1, it's a weak variable. You can exclude such variables. Apart from information value, we will do other checks as well, multi-collinearity check and all those checks, business sense, whether the variable is making business sense also. Sometimes a variable called mobile number, just by chance, mobile number shows good information value. Does that mean we have to include that mobile number? Do you think when you're making the decision, a person is a good person versus bad person? What will be the mobile number? Mobile number will be less. It will start with 8 for good customers. It will start with 9 for bad customers. Can we draw such conclusions?
No.
Though it is giving high information value, that happens just by chance. Do you agree with that point? It happened just by chance. That's why somehow it's a mathematical formula to show some variables doesn't make any business sense. We will drop them. Finally, we will select the variables that are having the high information value, that are not multicollinear, that are making business sense, that are having good predictive power. We will keep on dropping the variable. If you're starting with 400 variables, finally you will end up with 50 variables in some cases. After that, we went to information gain. This is an alternative for information value. We have also seen information gain in decision trees. We have seen this example. If you have the same income versus gender, if you have these variables, if you want to predict which variable is having or which variable is a driver on person buying or not buying, which is a strong driver, you can calculate the information gain. Information gain is high for a variable, then you would say that variable is a good driver. That we have seen very much in detail in the decision tree algorithm, the variable that is giving better splits. So information gain for income is 1%, information gain for gender is 45%. We will say gender is a better way. Now, what if X variable is categorical? Think about variable X, something like gender, which is male and female, or something like region, customer region, which is like east, west, north, south, or what else? Customer segment or customer type, blue card, red card, or some platinum card, something like that. The variable X variable is categorical. Target variable is continuous. Target variable is something like sales, something like loss percent, or something like the purchase value. If you have this Y variable, which is continuous, X variable is categorical, how do you find out whether it is a driver or not? Okay. So for this, we have to use something called testing of hypothesis. We will now discuss testing of hypothesis in detail. Until here, it is just a recap of whatever we discussed. From here on, the session starts. Testing of hypothesis. Let us see. Testing of hypothesis, you will be surprised. This is a very simple concept. Very simple concept. But in this concept, there are so many statistical jargons that are used. Because of these statistical jargons, because of these statistical terms or Greek terms that are used, people find it very difficult to understand. It's a very easy process. Let us suppose you have to buy 10 kg laddu. Okay. There is a function in your home. So look at this, all of you, try to participate. You have to buy 10 kg laddu. You go to a sweet shop. So the 10 kg is in front of you. And this is a new sweet shop. You have never gone there. You have to buy it. How do we do it? The person, the vendor, sweet shop owner says, sir, this is a good laddu, take it. Take all the 10,000, 10 kg laddu. Are you going to directly take it? Think about it. I mean, in reality, if you go to a sweet shop and you're buying 10 kg laddu, are you going to take it? What do you do?
No.
We will not
We
take
will
it.
Taste it.
We will
check it.
taste it, isn't it? All of us do that, isn't it? We don't want to take any risk. Do you agree? We will go to that shop. And I think sometimes even without we asking, since everybody does taste it, automatically the vendor also tends to give us one laddu. Do you agree? They give us a sample. We first assume that the laddu is good. That is our assumption. Do you agree? We assume that the laddu is
Yes.
good. Then we take a sample to taste it, isn't it? We test it. Imagine this laddu is good. That's what the assumption. And when we tasted this laddu, automatically we got that vomit sensation or we felt like puking it. Are you going to buy this? Or the taste is not good? Are you going to buy it? We are not going to buy. We are going to go to other shop, isn't it? Or as soon as we eat it, as soon as we eat that laddu, it tasted so good. Are we going to taste remaining 10 kg? Is it necessary? This one sample is sufficient, isn't it? Yes or no? Yeah. So if it is already tasting good, if it is tasting fresh, we will say, yeah, pack kar do bhaiya. This whole process is known as testing of hypothesis. Testing of hypothesis, we do it in our daily life. What are the technical jargons? That 10 kg laddu that you have, that is known as population. The whole population. And the assumption, what is our assumption? What did we assume? We assumed that laddu is good. That is known as hypothesis. Or in technical terms, it is known as null hypothesis. No conditions, null hypothesis. Hypothesis means assumption. Hypothesis means assumption, basic assumption. Are you clear on hypothesis? What is hypothesis? You assumed that the laddu is good. That is a hypothesis. Now to test this hypothesis, what did you do? Your hypothesis is, to test this hypothesis, we took a sample. What is a sample in the laddu case? What is a sample here? 10 kg laddu is population. Can you define the population? Is 10 kg laddu. And the assumption or hypothesis, what is the hypothesis? It is good. Taste is good. Now what are you doing to test it? In the process of testing, what did you do? You took a sample. In our case, what is sample?
One laddu.
One laddu, isn't it? Some 250 grams or 100 grams laddu. Then what did we do? We tasted the sample. Like we did the test using our own taste buds. We did the test. This we have to define it carefully later on in technically, mathematically. Then we take the final decision. We take the inference. We accept null hypothesis or we reject null hypothesis. Do you agree? We reject. When do you reject null hypothesis? That means you started with laddu is good. When do you reject it? Think about it. You have tested it.
Sample is bad.
If the sample is bad, isn't it? If the sample is bad, then we reject the null hypothesis. When do you accept the null hypothesis? If the sample is good. You have certain limits. Your taste buds have certain limits. If the taste falls in those limits, you will accept. Do you agree? If it falls beyond these limits, if it is too salty or if it is too sweet, then you are going to reject the null hypothesis. This is a very basic example. Let us take a real industry example. Let us go to a place where really testing of hypothesis is used. Have you ever heard of quality control team? QC checked, quality checked. Have you seen this stamp on any of the product? Checked.
Yes.
QC.
Yes.
Yeah. So that is after testing of hypothesis only they put this stamp QC, quality checked or quality control passed, isn't it? Let us suppose you go to Mysore Sandal soap factory. Okay. You go to Mysore Sandal soap factory. Let's say daily they are producing 1 million soaps. Possible, isn't it? They must be producing many more than that because they have the distribution across the whole India. So daily they are producing 1 million soaps. Now you are a quality assurance QA engineer there. Okay. Now on Mysore Sandal soap, it shows that this soap is 250 grams. The weight of the soap is 250 grams. All of you, look at this. 1 million soaps is the population. Okay. 1 million soaps are there. And Mysore Sandal is putting a weightage of each soap. Weight of each soap is 250 grams. Now you are a QA engineer. Tell me, How do you, so let's say it is up to you. You have to put this QC checked or quality control passed, and then only you can send it. It has to be 250 grams. Let us suppose by mistake, the average weight of the soap is 280 grams. That will be a loss for the company, isn't it? 30 grams extra you are giving for every soap. That will be a loss for company. Do you agree? Then you will reject this lot. There must be something wrong with the machine. Do you agree? Then if the soap is, let's say, 230 grams, what is the problem? If the soap is 230 grams, the consumers will put you in the court, isn't it? Because you're cheating the consumers. Do you agree? Is it possible a customer can take you to the consumer court because you are selling, you're saying that it is 250 grams, but you are giving 20 grams lesser. These things may look very small here, but some customers will be very serious. Do you agree? Yeah. So it will be a bad reputation for the company. So it has to be exactly 250 grams. 1 million soaps. Do you think there will be a weighing machine that can weigh all these 1 million soaps or 10 million soaps? Is it possible to weigh all these 1 million, 10 million soaps in one shot? That is not possible. Now, is it possible to take each of the soap? Take first soap, find the weightage. Take the second soap, find the weightage. Find the soap, find the weight. Is it possible going soap by soap? That is also not possible. So what is the population here? The population is 1 million soaps. That is the population. Can you tell me the null hypothesis? What is the first assumption? What is the null hypothesis here in this context? Each soap,
Each soap is of
250
250 grams.
grams.
each soap is 250 grams. That is null hypothesis. Let me pause here and ask you, have you understood the concept of null hypothesis? The basic
Yes.
assumption, our first assumption, basic assumption. What is your basic assumption here? Okay, each soap is 250 grams. That is the null hypothesis. Now, what do we do to test this null hypothesis? Are you going to consider the whole population, or what are you going to do? You take a
We
Take
will
the sample.
take samples.
sample, isn't it? Maybe out of 1 million soaps, let's say you can take 100 soaps. Make sense?
Yes.
If these 100 soaps are really coming from the population, this population where each soap is weighing 250 grams, what do you expect? The average weight of 100 soaps should be what? If your null hypothesis is true, what should be the average weight of 100 soaps?
250 grams only.
It should be 250 grams, isn't it? So what do? You take the average weight of 100 soaps. That is known as test statistic. You're finding the average weight. That is known as test statistics. Apart from average or the mean weight, what is the other test statistic that I can consider? One is mean
Median.
weight, or I can find the median weight also, isn't it? But can I find the standard deviation of the weight? Does it give me a good test statistic? Is it a good test statistic? We are not testing variance. We are finding the average weight. So mean or median should be fine. The test statistic is, what is a statistic? Statistic means something that is measured on the sample. What are you measuring? Average weight is what you are measuring on the sample. Let us suppose the average weight of the 100 soaps is 295 grams. 295 grams. Are you going to accept the null hypothesis, or are you going to reject the null hypothesis?
We are going to reject.
Why are you going to reject the null hypothesis? If it is
Because it's
really
not
true, what should be the average weight of the 100 soaps? What should be the average weight?
250 grams.
It should be 250. Is 250.5 grams fine? 0.5 grams extra. Is it fine?
No, because overall it would be a loss.
So 0.5 grams. Is that fine? Think about it.
Yeah, it is.
It is
Consider
fine,
that.
isn't it?
Maybe.
Yeah. 0 like 1 gram, that gram itself, if it is gold, then it matters. ये तो soap है, isn't it? Yeah, like 0.5 grams, half of the gram. That is not a big deal because it's a machine. When you are cutting here and there, the small things will happen. Do you agree? isn't it? Like
Yes.
the
Yes.
precision of
Yeah.
the machines, you can like, since it is soap only, soap material, people, the machines also will not be 100% accurate. So 250.5 grams is fine. 249.5 grams, is that fine? Will the customer
Fine.
be fighting for us with this? So little bit here and there. So 250 grams, 250 grams should be the case. A slightly higher than 250, slightly lower than 250, maybe until 252 grams, until 248 grams, you will be fine. Even the customer will be also be fine. As a company, we will be fine. As a customer, 2 grams, 3 grams, the customer will not fight. Do you agree? But if it is far away from, far below 250, let's say 230 grams, is it fine?
No.
That's not fine. 20 grams. 20 grams is almost like 10% of the 250. 10% weightage difference is too much. Do you agree? Is 270 grams fine?
No.
That is also not fine. So if 250 is the expected one, maybe somewhere around 250 is fine. Beyond that, if it is too far, we are going to define how far is too far. If it is too far from 250, far below or far higher, then we are going to reject the null hypothesis. Otherwise, if 250 is expected, 250.8, are you going to accept the null hypothesis or reject the null hypothesis? 0.8 grams extra. Are you going to accept or reject? It is less than 1 gram. So we are going to accept the null. What is the null hypothesis? Average weight is 250 grams. We are going to accept it. Okay. So let us see some more details. Let us discuss some more examples. So overall, this is also known as statistical inference. The inference has to be made on population. But to make that inference, what are we doing? From the population, we take a sample. Population average weight that we have considered in the previous example, that is known as population parameter. When it comes to sample, that is known as statistic. A measure that is calculated on the population is known as parameter. A measure that is calculated on the sample is known as statistic. So this is also known as the concept of statistical hypothesis. Okay. So what is testing of hypothesis? Whatever we are testing, that is known as hypothesis. What is a hypothesis? A verbal statement or a claim or an assumption about the population parameter. Is this hypothesis, this term, is it clear by now? Hypothesis, what is hypothesis? When somebody says hypothesis, will you be able to visualize it? Will you be able to understand by now? A hypothesis is a verbal statement or a claim or an assumption about a population parameter. About the population, we start with an assumption. That assumption is the hypothesis. How are we testing? How are we testing? Are we testing on the whole population? Do we have, is there a possibility of testing it on the whole population? That's not possible. That's why what do we use?
We use samples.
We use sample statistic. Let us take one more example. A CEO of a national bank claims that their employee average age is 35. Think about a bank like SBI. Everybody is trying to blame SBI, saying that the people who are working in SBI, they are very old people. The CEO of SBI, he says that, no, the average age of our employees is 35. Now, is it possible to go to each and every new corner of India, because SBI is present everywhere? Is it possible to take every employee and their age? Is it possible to find the average age? It's not possible, because SBI has nearly 3 lakh employees, even more than that. Getting the data of every employee will be very difficult. Okay. Now, what will you do? Now, tell me, what is the population size here in this example? Population size.
2,92,000.
So all the 3 lakh employees, isn't it? What is the null hypothesis? All of you think about the null hypothesis here. What are we testing? What is
35.
our basic?
35.
What is 35? Average
36.
age, isn't it? Average age is 35. Now, what are we doing to test this? What do we do to test this? Are we going to consider all the 3 lakh people? No, we take a sample.
Samples.
Let's say usually in statistical analysis, in theory, any sample which is more than 30 size is known as large sample. That is the academic definition. But usually what people say is large sample you decide based on the data that you have. Usually sometimes 1,000 is considered as a large sample. Sometimes 100 is considered as a large sample. Academically 30 is a large sample. Here we are taking a sample of 500 customers, which is sufficient, a large sample. A sample size here is 500 customers. Now tell me, what is the sample statistic that you are going to calculate, or the test statistic? What is statistic? Something that is calculated on the sample. What are you going to calculate?
Age.
Just age, average age,
Average
age on these 500 employees, isn't it? Okay. So 35 is what the CEO of SBI has claimed. If the average age is coming out to be 36, is that fine? Is that fine?
All right.
Yeah, that's fine, isn't it? Nearby it is 1, 2, that is fine. But if the average age of these 500 employees is coming out to be something like 45, are we going to accept the null hypothesis?
No.
If it is coming to be 36, are we going to accept it? Is it okay? See, he is claiming it to be 35 and we got the average, because we are not considering the full population. Tell me, isn't it? We are not considering the full population. 1-2% differences can happen. Do you agree? Since we are not taking all the 3 lakh employees, since we are taking only 500 in a sample, we can accept some little bit of error. 36, 37 may be fine. But if the average age is 45 here, then we are going to reject the null hypothesis. So here is the testing of hypothesis process. Assume that the population mean age is 35. Population average age is 35. This is the population, around 3 lakh employees. Take a sample, 500 customers. Find the sample mean. Let's say sample mean is 40. Is it likely that the population average is 35, but your sample will have average age of 40? Is it likely? If this is really coming from this population whose average age is 35, is it possible to get a sample mean of 40? Is it possible? Not
No,
likely, isn't
not
it?
likely.
So are you going to accept or reject? Is it truly coming from this population with average age 45? Not possible, isn't it? So you're going to reject the null hypothesis. Okay. So what are we going to do here? What is the reason for rejecting H0? H0 is known as null hypothesis. What is the reason? If it is really coming from a population where the average age is 35, then the average of these 500 customers should be 35 or 35.5 or 36 or maybe 34.5 or maybe 34 or maybe 36.5. But if it is 40, now that is not likely. It may not be true. The null hypothesis may not be true. Now, how far is really far? The only question that remains, all of you focus on this. The final question that remains, what is the question that is in our mind? 35, 36, it is fine. 34 is fine. Is 37 fine? Okay, fine. Is 38 fine? Is it near to 35? How far
No.
is really far? That we need to decide, isn't it? When do you say, in this range, I will accept null hypothesis. In this range, I will reject null hypothesis. How do you decide this range? That's the final question that comes to our mind, isn't it? Do you agree? Because
Yeah.
exactly 35 may not be possible. Do you agree, all of you? If population has an average of 35, exactly 35 in the sample also may not be possible, because sample may not be complete representation of the population. There might be few things that we may be missing. How do you decide how far is really far? For that, there is a concept called sampling distribution. What is sampling distribution? If you consider this whole population, from that population, if you keep on taking the samples, 3 lakh customers are there, right? Take randomly 500 customers, sample 1. Sample 1, find the average age. Take sample 2, again from 3 lakh, take sample 2, find the average age. Take sample 3, sample 4, sample 5, sample 6, sample 7, sample 8, like that. infinite number of samples, or maybe you have taken around 1 lakh samples. 1 lakh samples. For each sample, you found the average age in each of the sample. You know what? The distribution of this average age, all of you look at this. The distribution of the average age follows a normal distribution like this. What is a normal distribution? Most of the points, or most of the cases, the average will be around 35, and 30% of the times it will be in these limits. Around 60% of the times it will be around these limits. So it is known as central limit theorem. What is the central limit theorem? If you take a sample which is a large sample, usually academically large sample is a sample size more than 30. Let us consider 100. So if you take 100 number of records as a sample, and if you keep on repeating it infinitely many times, or maybe a million times, or 10 million times, or 1 crore times you have considered samples, and for each sample you find the average value, then you know what will happen. The averages, those averages will follow normal distribution. Most of the times, this normal distribution, most of the times will have whatever is the population mean. Mu is the population mean. There, that will be 35. It will be around this. And most of the times, most of the data points will be around this. Now, what do we do? If around 95% of the limits, 95% of the times, where this number will be, we will be able to find out. 95% of the times, the number has to be in these limits. This is the 5% of the times. 5% of the times, it can go to, let's say, 35, 36, 37, let's say 38, 34, 33, 32. 95% of the times, it falls in between 32 to 38. 5% of the times, it can go beyond also. Tell me one thing. If the average of the population is 35, is it possible for a sample, the average age is 55? Is it possible theoretically? Think about it.
No.
Think about it. Let's say you took an extreme sample. Let's say infinite times you have repeated, right? It is possible that there may be one sample where only all the elderly people are falling in that sample. Is it possible? All the 100 people you considered are all the elderly people only. That is where the average age is 55. Possible, isn't it?
Yes.
This is average. Yes or no? Let us suppose in SBI, there are 500 people whose age is 55. And in a sample, infinitely many times you have sampled, right? In a sample, everybody from that population only fallen. Is it possible the average age in a different sample is coming out to be 25 only? Is it possible? Theoretically?
Yeah.
Yeah.
Yes.
So extreme cases are possible. What is their chance? What is the chance of happening? Very high chance, very high likelihood, or very low likelihood?
Very less.
Low.
Very less likelihood, isn't it? It's as less as it will never happen. Is it possible for Indian cricket team to win next 5 World Cups continuously? Is it possible?
Very less chances.
It is possible, but the probability is very low, isn't it? We will almost say that it is impossible. Yes or no? The probability is so low that 0.00000001. We will say that it is almost impossible. Like that, it is possible until here 95% of the population is covered. The remaining 5%, let's say 2.5% here, 2.5% here. If the test statistic falls here, if the test statistics falls here, then we would reject the null hypothesis. If the test statistic falls here, we will accept the null hypothesis. We will take the decision based on the central limit theorem or the sampling distribution. The sampling distribution is the one that will complete this whole process of testing of hypothesis. So in short, you start with one assumption, null hypothesis. You select a random sample, assume that the sample you have is random. Usually we should not take a biased sample, isn't it? If you take a biased sample, what do you mean by biased sample? Intentionally you are taking all the young people. Are you going to take the sample, like say SBI manager itself, he gives you a sample, are you going to accept his sample? SBI CEO, he himself is giving you a sample. Take this sample and test it. Are you going to believe in him?
No.
There is no point there. We have to take a random sample, isn't it? Fair sample. You do the test on the same. How do you do the test? Calculate the sample statistic. If the sample is taken from the population, you expect the sample statistic to be in certain limits. We can find the 95% limits. If this is 35, 95% of the times it falls between 32 to 38. Just an example that I'm giving. If it is beyond these limits, if it is 31, are you going to accept or reject? Accept
Reject.
or reject. Null hypothesis. If null hypothesis is true, if it has to be here, isn't it? In these limits.
Yes.
If it is very
Yes.
far away, then you are going to reject
Reject.
the null hypothesis. The final thing, the distribution, the statistical distribution on the sample statistic, this will give us the way to decide the final thing. So there are 5 steps in testing of hypothesis. You start with making assumptions, which is null hypothesis. We state the null hypothesis. Select the sampling distribution. Maybe for the sample mean, the central limit theorem says that sample mean follows the normal distribution. But if you take sample standard deviation, or if you're calculating something else, if you're testing something else, it may not follow this normal distribution. Sometimes the distribution followed by the samples will be this one. So depending on what distribution that follows, we have to find out 95% of the limits. We compute the test statistics, then finally make the decision. If it is falling between the limits that we have thought of, 95% limits, then fine. If it is falling in this 5% limits, then it will be gone. Okay. Random sampling. First do the random sampling, 500 random cases that you have to take. State the null hypothesis. Once again, tell me what is the null hypothesis. The population mean, usually population mean is displayed by mu. Sample mean is displayed by x bar. Population mean mu is 35. Okay. So in other words, what are we saying? The average value on the whole population, there is no difference between sample mean and the population parameter. What is the alternative hypothesis? Mean is not 35. Mu is not equal to 35. Alternative hypothesis. Usually people don't talk about the alternative hypothesis. We have the null hypothesis. Either you accept null hypothesis, or rejecting means automatically you are accepting the alternative hypothesis. Mean is not 35. Then select the critical region. What is a critical region? If you see here, this is the region where you accept. This is that critical region. If the test statistic falls in this critical region, then you reject the null hypothesis. Okay. Let us go through these steps once again. So there is a formula. So the whole distribution that we have discussed, there is a formula to calculate the Z value. This is known as Z distribution. By calculating the Z value, we will be able to find the probability, and we will be able to find out whether it is falling in these ranges or beyond this. So finally, you will say that this much is where you accept. And if it falls here, here comes the concept of P value. Let us suppose these are your limits, okay, that you have accepted, and based the sample statistics falls here. Let us suppose this is 35, this is like 38, and the sample statistic value is 39. Okay. P value is from here, whatever is the probability from here, probability of having this number or beyond this, that is the P value. The P value is from here, what is the probability? Let us suppose if you take this one, this whole thing is 95%. From here, what is the probability? From here, so this one is around 2.5%. This one is around 2.5%. P value is from here, whatever is the probability. If this number is less than whatever is this number, if the P value is, let's say, 0, or if the sample statistics fall here, then the P value will be much more lesser than that. So probability of having 39 or more. Is it possible? 35 is the population average. Is it possible to have a sample of 39 average age? Is it possible theoretically?
Yes.
Theoretically possible. But what is the probability of happening it?
Very less.
Very less, isn't it? Then if the probability is very less, what will you do? If the p-value probability of having 39 or more than 39 is also possible, but what is the probability value or p-value of happening it? Very less. Let's say p-value is 0.0001. What will you say? Reject or accept if the p-value is very less? If the probability value is very less, you will accept the null hypothesis or reject. Think about it carefully. Try to recollect. If the probability of happening 39 or even more than 39 is very, very less, then are you going to accept or reject the null hypothesis?
We will accept because
Look at this. Let's say you got 39. 35 is the assumption. Are you going to accept null hypothesis or reject null hypothesis?
if it is 39, we will reject.
Reject, isn't it? Do
Yeah.
you agree? Because probability of happening 39, the probability of happening 39 is known as p-value. P-value is very less. That means what? It is far away. Do you agree? Let's say you got something like 36. What is the probability of getting 36 if it is coming from a population of 35? High or low? Is it possible to get many cases
Yes.
like this? So
Yes.
p-value will be high. P-value is, let's say, 0. Something like 0.30 or something. Are you going to accept or reject null hypothesis? If the p-value is high, p-value is what? Getting 36 or more than 36, which is very high. In this case, we are going to accept. Do you agree? Let us look at p-value once again. You are expecting the number to be somewhere here. You are expecting the number to be somewhere here. And you got the number, let's say, average age is 50. Is it possible? Null hypothesis is 35, but the test statistic X bar is 50. Is it possible? Theoretically?
Yes.
Theoretically possible. But what is the probability p-value for this event to happen?
Okay, well, less.
Very less.
Very, very less. Are you going to, if the p-value is very, very less, if the p-value is less than 0.05, then what will you do?
We can ignore.
Ignore or accept or reject null hypothesis from the null
Accept.
hypothesis? Accept null hypothesis or reject null hypothesis? Think about it carefully.
Reject. Yes.
Once again, let me write down. Let's say H0 is 35. Test statistic on the sample is 50. Is it possible to get 50? Possible means what? You will talk in terms of probability. Is there a probability of getting 50? It is possible, but what will be the probability value? P value will be what? That means 35 is here, 50 is here. Is it possible to get 50 or more than 50? Is it possible? Think about it. Think in simple terms. Average age is 35. On your sample, you got 50. Is it possible? Possible, but very, very less
Probability is very
probability.
less.
Probability will be very, very, very less. Lot of zeros, 1. Do you agree? If the probability value is very less, are you going to accept the null hypothesis or reject the null hypothesis? If the p-value is very less, that means, see, think about it. If the p-value is very less, probability value is very less, that means test statistic is very far away from the null hypothesis. If the test statistic
Yes.
is very far away from the null hypothesis, do you agree with that point?
Reject.
If the p-value is very less, that means the test statistic is very far away from the null hypothesis assumed value. So do we accept or reject? If it is
Reject.
far away, we reject the null hypothesis. That means maybe it is not coming from the population average age of 35. But what if you got X bar as 35.5? Is it possible? Population average is 30. Sample has an average age of 35.5. Is it theoretically possible to get like this?
Yes, very likely.
What is the probability of happening it? What is the probability p-value?
99%.
Yeah, very high, isn't it? Very high. Because if 35 is the one, maybe you can get slightly less than 35, maybe slightly more than 35. Let's say the p-value is 0.40. If the p-value is high, that means statistic value and the population mean. Like p-value is what? From here, let's say 35.5. What is the probability of getting 35.5 or more than that? Now that probability is, let's say, 40%. That means these two are very near to each other. Then what do we do? Accept or reject the null hypothesis? Think about it.
Accept.
We accept the null hypothesis. So we finally find something called p-value. This p-value will tell us if the p-value is usually less than 0.05. That means the test statistic, if the p-value is less than 0.05, what does that mean? P-value is very less. That means test statistic and the population are very far away. Then we reject the null hypothesis. Reject the null hypothesis. If the p-value is more than 0.05, that means test statistic and the population mean are somewhere in the permissible range. We accept the null hypothesis. Let us look at it once again. The population average age is 35. We took a random sample and we found the average age to be around 40. But it is very extremely unlikely that the sample age is 40 if it is coming from a population age of 35. Do you agree with that? Extremely unlikely means what? The probability value is very, very less. It is less than happening 1 in 1 billion. That means it is even less than India winning next 3 World Cups. Then we will reject the null hypothesis. How did we find the probability here? Because we have this distribution, normal distribution. What is the probability of, let's say if 35 is the population, what is the probability of sample getting something like 40 and more than 40? That we got it from the center limit theorem. Okay. If you go to regression, there also we used p-value. Then I told you that p-value concept comes from the testing of hypothesis. So there the null hypothesis was beta I equal to 0. Beta I equal to 0. What does that mean? The coefficient of a variable is equal to 0. Beta I is 0. That means what? This is 0 means the variable has no impact. Think about it. Is that true? If I take a variable and its coefficient is 0, what does it mean? That variable has no impact. That's a null hypothesis. The alternative hypothesis is this. Under the null hypothesis, we found the test statistic. Finally, it will come down to the p-value. Let us suppose you take variable x1, whose p-value is 0.30. You take variable x5, whose p-value is 0.006. x1 p-value is 0.30. If the p-value is more than 0.05, look at this. Let's say here is x1 variable whose p-value is around 0.30, 30%. 30% is the p-value. Are you going to accept the null hypothesis or are you going to reject? If it is here, are you going to accept or reject the null hypothesis?
Accept.
We will accept the null hypothesis. If you are accepting the null hypothesis, what is that you are accepting? If you are accepting the null hypothesis, what are you finally going to talk about? X1?
That is
Accept null. What is your null?
35.
X1 has impact or no impact? If you are accepting null hypothesis, you are accepting that beta I is 0 or beta 1 is 0. Look at this. Impact or not impact? If you are accepting
impact.
null, no impact. Do you remember at
No
that
impact.
time, if the p-value, do you remember in regression, if the p-value is greater than 0.05, what did we say? Impactful or not impactful?
No impact.
Not impactful. Do you remember it? So behind the scenes, the p-value is calculated. Here, the null hypothesis is on no impact. Beta is 0. Then based on that, only test statistic is created. Come to x5 variable. If for x5 variable, the p-value is 0.006, 0.006, very, very small number. That means, are you going to accept null or reject null in this case? If the p-value is very less, think about it, all of you. P-value very less. That means what is the
Reject.
expected value? Whatever we got, they are far away from each other. If expected and the result is far away from each other, are we going to accept or reject the null hypothesis?
Reject it.
Reject null hypothesis. So here, if you reject null hypothesis, that means you are rejecting that there is no impact. That statement you are rejecting. Then what are you accepting? What are you accepting?
It is impactful.
If the variable is impactful. Do you remember, if the p-value is less than 0.05, the variable is impactful, we keep it. Do you remember it from the regression? From the regression examples? For
Yes,
in
yes.
regression, if you go to regression, if the p-value is greater than 0.05, then we reject null hypothesis, or we simply say we drop such variables. Do you remember it? If the p-value is less than 0.05, then we keep such variables. Can you recollect this from regression? Behind the scenes, this particular testing of hypothesis was done. Finally, p-value was calculated. Final inference was made based on that. The variable impact was calculated in regression. So here in testing of hypothesis, though it looks like testing of hypothesis and all that, it is a simple process. Whatever your population is, you take the population, and then you test the population using a sample statistic. In this whole process, the concept of sampling distribution. So where is that region where I'm going to accept? Where is that region that I'm going to reject? That will be decided based on the concept of sampling distribution, where we need to find for each test statistic what is the right sampling distribution. But there can be some errors that we will be making in the testing of hypothesis that we need to understand. There will be two types of errors that we will be making. Think about it, all of you. There can be two types of errors that we will be making. For example, you have rejected the null hypothesis. Sometimes the null hypothesis may be correct, but you still have rejected it. Tell me one thing. If the average age is 35, is it possible to get 39 on the sample? Is it possible?
Yes.
Possible, isn't
Yes,
it?
possible. Yeah.
But what did we say? That the possibility is very less. That's why I'm rejecting the null hypothesis, isn't it? Yeah.
Yeah.
But that small portion, maybe genuinely your sample itself is wrong. Genuinely 39, like genuinely 35 is the average age, but you still got 39. Is it possible? That means that's a mistake on our side. Do you agree? Think about it. Is that a mistake? Do we do some mistakes? 5% of the times we are making such mistakes, isn't it? This is the whole distribution. In this distribution, this one we are rejecting, this one we are rejecting. But are they possible? These are possible, but still we are rejecting. That is rejection error. That is known as type 1 error. The other error is acceptance error. What is acceptance error? The actual average age is 40. But the sample that we have taken is having average age 35. You took a sample, average age is 35. Are you going to accept or reject? Think about it. Though the overall population average age is 40, we are testing the assumption that 35 is the average age. And in our sample also 35 is shown. That is acceptance error. That means by mistake, based on the sample, you are accepting wrongly. Since we are working with a sample, you may be doing two types of mistakes. Let us look at these errors. Let's say the null hypothesis is, am I pregnant or not? Let's say some testing was done, some blood test was done. At the end of blood test, look at the scenario 1. After the test, the first doctor is saying, sorry, you are not pregnant. Is it possible? The test is done on some parameters. It has to fall in certain parameters, and the parameter falls here. Possible? So they
Yes.
rejected it. Okay. Now, by mistake, his blood sample was taken. For this person, it is falling inside his boundaries. He has been judged as, yes, you are pregnant. Possible. Both the cases are possible, isn't it? You are
Yes.
expecting the value to be certain limits, and sometimes you are rejecting, wrongly rejecting H0. This is known as rejection error. So H0, am I pregnant or not? Okay. So you're wrongly rejecting H0. That is type 1 error. Wrongly accepting H0 is known as type 2 errors. So we have to manage both type 1 and type 2 errors carefully. We have to make sure that we have less type 1 error as well as less type 2 errors. Okay. So these are the two types of errors that may happen on testing, because we are working with a sample. We are not working with the whole population, and we have to live with this because it is impossible to consider the whole population. Okay. What we will do is, to understand this testing, we will take a particular example and try to understand the code behind it. So sometimes your H0 is true. In some scenarios, your H0 is true, but we are going to reject it. So that is type 1 error, rejecting when it is true. Sometimes your H0 is false, but still we are going to accept it or don't reject it. That is type 2 error. Okay. So which one is bad? Both type 1 and type 2, both are bad. We have to avoid this by taking the right sample. Look at this, all of you. Your sample should not be biased. If you take a biased sample, then you may get into these kind of errors. What do you mean by biased sample? You want to prove something and intentionally you are taking a biased sample, then you will get into these errors. You have to avoid these errors by taking a totally random sample, the right representation of the population. Taking a slightly larger sample, you will be able to avoid these issues. This whole process is known as testing of hypothesis. Before going to an example discussion, we will take the questions now. Any questions, anybody?
Sir,
Yeah.
I have a question.
Yeah.
Sir, when we discussed about our regression models, we said that p value greater than 0.05, we will be dropping it, right? So those
So
are
p value.
not...
So let us take step by step. P value greater than 0.05 means the variable is not impactful. So in
Not
regression, behind the scenes in regression, the null hypothesis is this one. What is the null hypothesis? The null hypothesis is no impact. Beta I is 0. Okay. Beta I is 0. That is the null hypothesis. Okay. Now alternate hypothesis. So null and alternate hypothesis are clear here. What exactly test has happened? Now let us see p value for a variable. Let us take variable x1. Let us take variable x5. For this variable, the p value is 0.0005. For this variable, the second variable, the p value is 0.3. Okay. Now let us talk about, are you talking about x1 or x5?
x5.
x5. x5 has a p value which is greater than 0.05.
0.05.
So
Yeah.
here x5 variable has a p value greater than 0.05. Are you going to accept null hypothesis or reject? First tell me from the testing point of view.
Testing point of view, with your explanation, we will be accepting it, sir.
Accept. So go to null hypothesis. Tell me what are you accepting here? Read the null hypothesis. What are you accepting?
Null hypothesis, beta equal to 0 is no impact. Beta
So,
not equal to 0 is
null hypothesis. Null hypothesis H0.
H0. Yeah.
Yeah. The second one is alternate hypothesis. So read the null hypothesis. Null hypothesis beta I equal to 0.
Equal to
Means
0.
the variable has no impact. That is what we are accepting. So the variable has no impact. X5 has no impact. If a variable has no impact, what will I do? If a variable has no impact, what can we do? Drop such variables?
Yes.
Yeah, we can drop it. If a variable has no impact, if it's beta coefficient, beta 5 is almost 0, we can drop such variable. That's what we also discussed in regression. If a p value is greater than 0.05, what do we do?
P value greater than 0.05, we drop it.
Drop. Make sense?
Yeah. Sir, but one thing what is confusing is here in hypothesis, p value greater than 0.05 is lying extreme place, but
no, not extreme. P value greater than 0.05 is lying nearby. Yes or no? P value greater than 0.05. Think about it. What is p value? let's say if the number falls here, then the probability will be very less, isn't it? Less than 0.005, less than it will be, yes or no? P-value greater than 0.05 means what? It falls somewhere here, isn't it? P-value 0.3 means what? It will be somewhere here. This whole thing is the P-value, yes or no? So for X5 variable, P-value is 0.3. Yeah. So first talk from the regression point of view. For a variable X5, P-value is 0.3. What did we do there back then in regression?
We were dropping it.
We dropped that variable. Let us check, are we consistent in this or not from the testing point of view or not? That's what you want to check, isn't it?
Yes.
Let's talk about testing. P-value of a variable is 0.3. In testing of hypothesis, P-value is 0.3. Do we accept or reject null hypothesis? First, let us think about it.
Okay. We reject it.
P-value 0.3. Think twice. P-value 0.3.
P-value 0. In point of regression or testing you are asking?
Testing. In testing, P-value 0.3. 30% is the
P-value 0.3. We reject it. Sir.
Think once again carefully. P-value is high. If the P-value is high, that means the value is near to the expected one. This is expected. This is what you got, isn't it?
Yes.
Are you convinced? Think about it. P-value high means what?
P-value high is it is closer to the mean.
Closer, isn't it? P-value low means what? P-value is very, very less means what? What is our expected value and the real value? They're far away. Then we reject.
Yeah.
But in this case, what do we do? P-value is high. From the testing point of view, what do you do if the P-value is high?
We accept it.
We accept the null hypothesis. So right now, you say accept the null hypothesis. Is it clear until here? Accept null.
Yes.
Yeah. For variable X5, accept null. So tell me what is null hypothesis H0, null hypothesis. What does it mean? Accepting null means what? Accepting beta naught is 0. Is that what is accepting? Yes?
Yes. Yes.
Which means accepting that there is no impact of this variable. Is that correct?
Exactly.
Which means if the variable is not impactful, what will you do? X5, what will you do? Drop or keep? The variable is not impactful.
We will drop it.
Drop. So here also we are dropping only?
Yes.
So there also we are dropping only? Think about it. In fact, that is nothing but this process only. Whatever we discuss, this happens in the background. Now is that clear? Will you be? Yeah, please try to phrase the question now. Think about it.
Yes, it is clear, sir. But on a logical thinking, whichever is far away from the mean, it won't be impactful, right? That's what I am trying to relate that question. Because to me, whichever is farther than mean. That won't be.
What we need to discuss is the null hypothesis. What are we defining? Here, the null hypothesis is no impact. So from that point of view, if it is farther than impact, right? Null hypothesis is no impact. That means closer means no impact. In this case, it is opposite, isn't it? Yes or no?
It is opposite. Yeah, that's what I am trying to know. But major distribution will be happening in this no impact region, right?
Because we started with this assumption. What is our assumption? No impact is the assumption. That means closer means no impact. Are you with me? Farther means impact in this one. Because the null hypothesis is no impact. Because the t distribution that you have got here, the test statistic and all those things that are defined based on this null hypothesis. What is the null hypothesis? No impact is the null hypothesis. Okay. That is the reason why if the p-value is more, that means it is close. Since it is closer, that's why no impact. I think that last point is the one that is sounding counterintuitive, isn't it? Closer, no impact. Why? That's what you're thinking, is it?
Yeah, exactly.
But now is it clear? Because closer, no impact. Because the null hypothesis itself, closer means you're closer to this assumption. That means it is no impact. Okay. We started with this null hypothesis. This distribution was created with this null hypothesis. Maybe if you start with this null hypothesis, closer means impact. Beta naught is impact. Beta 1 is not impact. Then this distribution will change. It will not be T distribution. It will be some other distribution. Then maybe it will be farther. Okay. Farther means no impact. Closer means impact. That will be a different distribution, but that has not been proved. Like with this one, closer means no impact. Farther means
No.
impact. Yeah.
Okay. So farther means impact.
Yes. Farther means impact, because farther means we will reject the null hypothesis. We accept the alternative, which means like impactful. Farther means p-value is less. P-value is less than 0.05. That's why we keep such variables. We accept the null alternative.
Okay. So we keep such variables and then trying
First you
to
start
fit
with
in.
First you start with the hypothesis only. Based on the hypothesis only, your distribution will come. Okay. If your hypothesis is x bar equal to 50, that follows normal distribution, let's say. If your hypothesis is variance of x, that means the variance in the age is, let's say, 5 years. The same variance in the sample will not follow normal distribution. It will follow something else. To test variance, some other f distribution or chi-square distribution will be used. Based on that sampling distribution, we have to find out. Okay. That sampling distribution, we need to know for which hypothesis, what is the sampling distribution. It changes. Sampling distribution means what? If you keep on taking the samples, keep on finding their variances, it will form a distribution. Not always it has to be normal distribution. Okay.
Okay. Okay. And sir, to make it more relatable to the regression, we accept those whichever is farther. And finally, we will what we'll be doing, sir? We will be accepting it, and then we'll be further checking the multicollinearity and then finding
all those steps. Yeah. So this will
finding
be
the accuracy.
correct. This will be a kind of a single step in variable selection. Testing of hypothesis, its connection to regression is, in regression we have discussed 5 or 6 steps, right? One of the step was finding the impactful variables. To find the impactful variables, we use the t-test, and t-test finally gave the p-value. Okay. So this contribution is one of the steps. Like this particular one in regression, we do it as one of the steps in variable selection.
Okay, sir.
The same thing was done in logistic regression as well. For variable selection, the same test was done, and then based on the
we do the same for the regression. Yeah, logistic regression.
Correct.
Yeah. Okay.
If we have to take an example, it will look like this. If you go to Roseman store sales data, let us suppose my hypothesis is the average number of customers. Let's say 750 are the average number of customers. That is a hypothesis. I am claiming that to my store on an average every day 750 customers are coming. How do you prove or disprove it? I don't want to take the whole population. What we will do? We will take a sample. We will take a sample and we measure the average number of customers in the sample. And we find the p-value. What will be the null hypothesis in this case? Average number of customers mu equal to average number of customers mu equal to 750, and then we take a sample. For that sample, we will find the average number of customers. If it is 750, we expect it to be 750. Maybe we will find the limits. How do you find these limits? How do you find the critical region and all that? Based on the sampling distribution, then you will finally find the p-value. If the p-value is very less, all of you try to understand. If the p-value is very less, very small, what does that mean? The expected value and our value are, if the p-value is very less, very minuscule, the expected value very far. If the expected value and our value are far away, then are you going to accept or reject the null hypothesis? You expect it to be somewhere, but it is very far. So are you going to accept or reject?
Accept.
Think about it. If the expected value, whatever you are expecting, it is very far, then you will automatically reject, isn't it?
Reject it. Yeah.
Isn't it? Do you agree? Is there any confusion there? If the p-value is less, the connection that I want to create is p-value is very less, p-value is very less, then the expected value and the value that you got from the sample are very far. Then are you going to accept, like in that cake example? Like you are expecting it to be in certain taste range. If it is very bad, are you going to accept the null hypothesis that the taste is good, or are you going to reject the null hypothesis? We reject it, isn't it? Similarly, if we are expecting it to be in certain range, if it is very far, then we reject it. Okay. Similarly, the other hypothesis that I want you to test is, that is the first test. Okay. This is the first example. The second example is about the sales. The average sales is 5,600. We want to test whether it is higher than 5,600 or lower than 5,600 or near to 5,600 is what we want to test. Okay. This is the test for single mean. Let us do this testing of hypothesis. Let's go to our classroom, this session of driver analysis. Let me paste the link in the chat window. Driver analysis and testing of hypothesis. Here is a code file. I have pasted the link in the chat window. Go to your code file. Execute all the pieces of code from the previous topics. Directly reach to testing of hypothesis. After executing, stop at testing of hypothesis. Execute bar charts and all the correlation. Everything else you can execute. Continuous versus categorical, bank marketing data, credit risk data, WOE, information value. All those things you can execute. Information gain. Come to the testing of hypothesis topic. What I want you to do is, I want you to test. Take the sample, take 100 records, take 100 records. And why do we use random state? Let's do one thing. All of you stop at testing of hypothesis, execute everything else, stop at testing of hypothesis. Send me a message once you are here near the testing of hypothesis topic. Yes. Can you see my screen? For me, it is executing information gain. Done. Come to this testing of hypothesis. So here, the first test that we want to do the testing upon is the average number of customers is 750. Is that true or not? This is what we want to test. So I'm taking a random sample of 100 records. Can somebody tell me, why do we use this extra parameter called random state? What is the reason for using it? Any idea why this random state is used? If we want to generate the same sample again and again, for example, if I do like this is a sample without random state. If I create a sample, every time I execute it, I get a different sample. Let us see here, store ID is 729 in the first row. If I re-execute it, I'll get a different sample. 999 is the store ID. I'll get a different sample. 853 is the store ID. Everyone will get a different sample. How do you make sure that I get a sample, random sample, but I want to regenerate the same sample again and again. Then you can use seed, or here it is known as random state. If you give this random state parameter and all of us mention the same ID, this ID doesn't matter. Any number you mention it. No matter how many times you execute it, according to this seed, the same random sample will be generated. Look at this. 953 is the store ID. Once again, if I execute the same 953, the same sample will be generated. That's why I want everyone to get the same sample. That's why we are giving some random state value, which is same. I want to do the Z test. This is known as testing for the population mean, or Z test. Normal distribution is also known as Z distribution. That bell curve that you see, that is known as normal distribution. That is a sampling distribution when we take multiple samples. So finally, we want to get Z test and P value. If the P value, so go ahead, test for this sample statistic, the whole null hypothesis. Let's say first test for 700. Tell me, are you going to accept or reject this null hypothesis? If the null hypothesis is average number of customers is 700, are you going to accept or reject this? First test this one, all of you, and tell me, are you going to accept or reject it? Average number of customers is 750. Are you going to accept or reject this null hypothesis? Yeah. So if we want to do that, so take value is 700 and then get the test values, get the P value. P value is very less. All of you think in this direction. P value is very less. Immediately what we should think? P value very less than 0.05. What is the next chain of thought that we should get? Whatever is we are expecting, whatever the value that we got from the sample, they're far away or close to each other?
They are far away.
They are far away. Our expectation and from the sample, they are far away. What does that mean? Reject or accept the null hypothesis?
Reject.
Reject the null hypothesis. Makes sense? Think about it. If we say the average number of customers is 750, the P value is 9.20 into e power 0. minus 0.5. What does that mean? E power minus 0.5 means what? Divided by 5 zeros. That means it is 0.0009. 0.409. If you have the P value 0.409, P value is very less. What does that mean? P value less. Our expectation and the result are far away from each other, which means reject the null hypothesis. Okay, that is the example. Let's say if we are testing for, let's say 650 customers. Tell me, does that work? 650 customers. For 650 customers, the P value is 0.19. Think about it. 0.19. P value is more than 0.5. P value high here. When do you say P value is high? In which scenario P value is high? P value is greater than 0.05. That itself is high. So P value is high. That means expected value and the actual value that we got from the sample are near to each other. What do we say then? What do we do? Accept the null hypothesis. So that is the process. Similarly, you can do the same kind of test on the average sales as well. Test it whether it is sales is average 5,600. This is for single mean. You can also do some other tests. Let's say when you're testing two means, population 1 versus population 2, are they having the same mean or not? Let's say you have 500 or let's say you have a population. We want to say on an average, male are getting more salary than female. Or the null hypothesis is no, male and female are paid fairly. They are getting the same salary, but somebody is want to test it. Let's say in this bank, they are not paying same way. They are doing the discrimination. How do you test it? You take two samples, male and female, then mix them, find the average salary of male, average salary of female, then compare it. That is also done by z-test. Z-test for two means, z-test for population or proportions. Then if you have multiple classes, if you want to test the mean across several groups, that is known as f-test, t-test, chi-square test of independence. Like that, there are so many tests. At the end of the day, all these tests end up with the p-value. P-value will decide whether we should accept the null hypothesis or whether we should reject the null hypothesis. Let us do a couple of more examples. So here we want to do z-test for two means. This is the test statistic, and then it will give the population distribution, sample distribution. Look at this in the Roseman-Stokes-Dale data. Understand the problem statement here, all of you. When there is a promotion, that means promo equal to 1. When you are running some promotion, there is some sales. When you are not running any promotion, that means when the promotional offers is 0, this means no promo. This is, yes, some promotional, some offers were given. So you have the sales here, average sales. You have the average sales here. I want to know whether they are significantly different or whether they are same. What will be our null hypothesis? Tell me in this case. What is the basic assumption that you start with? Promotion versus no promotion. The sales is
more in promotion.
sales is same. You start null hypothesis means you will not, you will go with without any big thinking. Null means without any assumption. Simple basic assumption is sales is same. Alternative is sales is not same. Okay. Sales is not same. So here the null hypothesis is the difference is almost 0. The difference, there is no difference or negligible difference. So go ahead, test it and tell me whether there is any significant difference or not. Okay. Go ahead, test it, find the p-value. Based on the p-value, tell me what is the p-value that you got. So if you go for testing of two means, promotion 0, promotion 1, okay. For these two, you're finding the sales. For these two, you're finding the average sales, and the p-value is 2.99 e to the power minus 0.7. That means p-value is 0.000002. After 6 zeros, you will get a 2. Are you going to accept or reject? P-value is very less. P-value less. You have to imagine this diagram. P-value less means what? You accept the here.
Reject it.
P-value is very, very far away. So reject null. If you are rejecting null, sales is same, that you are rejecting. What are you accepting? Sales is not same. That means promotion versus no promotion. Is there any impact of the promotion or it's the same sales? Think about it. Is there any impact of the promotion? Definitely there is some impact.
Yes,
Yeah,
impact.
because the sales is changing. Similarly, do the same job for school holiday. When there is a school holiday, when there is no holiday, do you see a huge difference in the sales? When there is a holiday, what is the sales? When there is no holiday, what is the sales? Is there any huge difference? Do a test for that as well. Go ahead, do the test for that as well. Yep. Tell me, based on the second example, based on the second test, is there any impact of school holiday or the sales is same on the holiday versus no holiday case? You get that? Yeah. What is the result that you got? So instead of accepting or rejecting the null hypothesis, tell me from the point of view of business, like school holiday versus no school holiday. School holiday versus no school holiday. Is the sales same or is the sales different?
Sales different.
Difference. That means, so let me also see that. So if I go there, so here, so this one you have to write the code. It looks like, have you written the code for it? So here we have to write school holiday. What is the variable name? Have you written the code? Has anyone written the code? If you have written it, just quickly paste it in the chat window. I'll also paste it. I'm searching for the variable name. Here is the data. School holiday. This is the variable name. 0 versus 1. I'll go here. Testing of hypothesis. First tables and then testing for 2 means. Here is the code. School holiday 0 versus school holiday 1. Then as usual, I'll go ahead, execute this. So the p-value is 0.07, which is more than what? Which is more than 0.05.
05.
So what we will do? We will accept the null hypothesis. That means school holiday versus no school holiday. There is not much difference of sales. Whereas promotional versus no promotion, is there a difference of sales? So what I want you to finally answer is, when there is a school holiday, does your sales change? Holiday versus no holiday. Is there a difference in the
No.
sales? No
No.
impact of school holiday on sales. Do you agree? On a holiday versus no holiday of school, no impact. What about this one? When there is a promotion offer that you're running versus no promotional offer running, is there any difference in the sales?
Yes.
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 There is a significant difference when you're running a promotional offer, when you're not running a promotional offer. Okay. So this way you can tell these variables, the categorical variables, which are promotional offer 0 or 1, school holiday 0 or 1, versus target variable sales, whether there is an impact or not, using the testing of hypothesis. You can also do the testing for multiple means. That means if you have 4 or 5 categories, region 1 sales, east sales, west sales, north sales, south sales. Overall, is there any impact of region on sales? That means in a particular region, sales is high. In a particular region, sales is low. Is it like that? Or no matter what is the region, sales is same. If you want to test it, the same Z test will not happen because that sampling distribution changes. We have to do a test called F test. When you do the F test, more than 2 categories are there, you have to go for F test. In the same Roseman sales data, store types A, B, C, D. What I want to know is, does it matter whether the store type is A or B or C or D? Does it matter, or the sales same across the same thing? What you will do is, you will do the F test. Based on the F test, you will find out whether you will finally come up to the p-value. What is the null hypothesis usually in these cases? All of you think about the null hypothesis usually in these cases. Null hypothesis usually, whenever you are comparing like this, A, B, C, D, region, east, west, north, south, what is the null hypothesis that you come up with? What is the sales here? 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 The null hypothesis is sales is same or sales is different? Same is the null hypothesis. Usually sales same is the null hypothesis. Alternative hypothesis is significant difference is there. Any of these two, they have a significant difference. Test this null and alternative hypothesis. Tell me across A, B, C, D, do you see same sales, or is there a significant difference in the sales? So let me go there to that code.
Significant difference is there.
Difference is there, which means based on the p-value we have to tell. So go to testing multiple means A, B, C, D. So what do? The p-value is 0.42. If the p-value is high, what do? You accept the
it.
null. What are we accepting? Accepting null means what? Same
are
sales.
same.
All are same,
sales.
isn't it? No significant difference. All are same. That's what we are accepting. Okay. We are accepting the sales is same. Or if it is a weekday versus weekend, day of the week, 2, 3, 4, let's say day 2 means, let's say Monday, this is okay. Day 3 means Tuesday. Day 4 means or let's say day 2 Monday, Tuesday. Day 4 is Wednesday. Is there any difference between these 3 days, or the sales is same? Usually what is the null hypothesis? I'm talking about the sales.
Same.
Null hypothesis, same sales. Monday, Tuesday, Wednesday, doesn't matter. Alternative hypothesis, difference in the sales. Go ahead, do this test and let me know whether the sales is same or whether the sales is different. Whether the sales is same.
Sales is different.
Execute this. P got the p-value to be slightly less than 0.05, p-value less than 0.05. We reject the null hypothesis. We reject it. So we accept that sales is different. So the day of the week does matter. But the store type, does it matter? Does the change sales change based on store type? No, whether it is A or B or C or D. But does the sales change based on the day? Whether it is Monday, Tuesday, Wednesday, does it matter?
Yes.
It does
Yes.
matter, like that. Okay. So that is the testing of hypothesis. In fact, categorical versus continuous, we can also do it for using information gain value. We have anyway seen information gain. The last one is categorical versus categorical. The reason why I'm covering all these type of data is maybe in the case study that we are going to get, we cannot really see what type of data we will get, what type of X variable, what type of Y variable you will have. No matter what X variable, no matter what Y variable you are going to get in future, you should be able to do these insights. X variable is categorical. Something like, what is categorical X variable? Something like gender, something like customer region, east, west, north, south, customer gender, male, female. Y variable is also categorical, something like buying or not buying, something like fraud versus non-fraud. How do you find the relationship? What do you do in terms of visualization? And how do you quantify the type of relationship, whether they are interdependent or not, whether this is a driver or not? This whole thing is driver analysis, whether this is a driver or not. From the point of view of visualization, let us suppose if you have the target variable, whether the customer will buy a product or not buy a product, and you have another variable called customer education, secondary, tertiary, unknown, primary. So for each of these, you can create a bar chart. Within that, you can show zeros and ones, zeros and ones, zeros and ones. Okay. So visualization is not a very big thing. Or maybe you can show 2 bars as well. Let's say 1 bar for 0, 1 bar for 1 in each category. So here it is a customer job. Based on the job, is there any particular job where zeros are more than ones, like that? You can show the visualization, but when it comes to the actual quantification, that's what we are interested in. Or you can also show a cross tab. What is a cross tab? Here you have the customer job. How many customers have accepted or purchased the product? How many customers have not purchased the product? Or you can think of 0 and 1 customers are good customers, bad customers. And what did you highlight in this? Maybe is there any particular job type where there are more percentage of good customers, less percentage of bad customers? What is the general pattern? And is there any particular job type, higher good customers or lower bad customers are there, that you can highlight in these visualizations? But what really matters is you have to quantify the relationship. To quantify it, we use another test called chi-square test of independence. This is an important one. Chi-square test of independence. Let us suppose, so how do you do this chi-square test of independence? Let's say you have two variables. One is gender of the student. The other one is exam result. The gender is male and female. The exam result is pass or fail, pass or fail, pass or fail. How do you know whether exam passing has anything to do with gender? Let us suppose 600 students have passed, 400 students have failed in an exam. Let us suppose there are 500 male students, there are 500 female students. Look at this. This is the table that we got. 500 male students are there, 500 female students are there. The pass percentage is 60% of the people have passed. Tell me one thing, male, female, if it doesn't matter, all of you think about it. A person being male or female doesn't matter. How many male will be passing, how many female will be passing? Overall pass percentage is 60%. Out of male, how many will be passing, how many male will be failing? 60% out of male, isn't it? What will be that? 300 male will be passing, 200 male will be failing. Do you agree? In female also 300 female will pass, 300 female will fail. Do you agree? Tell me, because gender doesn't matter. Yes or no? Whereas if the table is like this, 500 are male, 500 are female. Look at this. Out of 500 male, 100 have passed, 400 have failed. Okay, total 500 male, 100 passed, 400 fail. 500 female, 500 have passed, 0 fail. Tell me, is it fair to say male, female doesn't matter? Passing or failing doesn't depend on being male or female. Do you agree?
No.
Is this the case here? Tell me, think about it carefully. If a
Clearly
student
says that female are
passing, isn't it? Tell me honestly, if male and being a male, being a female, if it doesn't matter, out of male 500, how many will be passing, how many should be passing? What is the expected value here? What is the expected number here? How much do you expect here? 60% pass, 40% fail. So out of 500 also 60% pass. How many do you expect here?
300.
300. How many do you expect here? 200. Out of female, how many do you expect?
300.
300 here? 200. Then it is fair to say, isn't it, whether a person is male or female, it doesn't matter, because in male also 60% pass percentage, in female also 60% pass percentage, isn't it? Yes or no? But here in male, what is the pass percentage? 20%. Fail percentage is 80%. In female, pass percentage is how much? How many people are passing in female?
100%.
How many are failing? 0%. Now tell me honestly, 20% pass versus 100% pass. Is there a difference? Do you think being passing or failing, there is some impact of being male or female here, isn't it? So the expected is this one. When exam result is independent of gender, this is what you expect. Answer me, is that correct? Try to acknowledge this. When the exam result is independent of gender, independent. When it is independent, you expect this table. Do you agree?
Yes. Yes.
But if male and female, if it is like this is very far away from this table. This is expected. This is observed table, isn't it? You should have got 300 here. You should have got 200 here. You should have got 300 here. You should have got 200 here. So what do we do is we find the difference between expected and observed. So here is the formula. The chi-square formula is observed, frequency of observed, frequency of expected divided by overall expected. So if there is a huge difference, let us suppose the result 10 table is like this. Ignore these numbers. Let's say there is 310 here. There is 190 here. There is around 305 here. There is 195 here. Expected values are 300. Instead of 300, you got 310. Instead of 200, you got 190. I think here you cannot put 195. Yeah. What should be? It should be, let's say, 310. And out of this 310, you would say like 290 is here. And then around 210 is here. Instead of 300, it is 290. Instead of 200, it is 210. What do you say, male and female? Is it independent of passing or failing? This is a perfect one. Is it okay, this one? Think about it. Is this fine? Or here also you will say male are passing more perfectly, very, very high, significantly higher than female, or almost same. Think about it. Gender, does it impact? Gender, does it matter? Being male or female? Almost same, isn't it?
Almost same, yes.
Here also almost same, isn't it?
Same.
So if it is near to expected values, almost same, it is far away, then you would say dependent. So here, if the results are like this, then independent. If the results are like this, then dependent. Dependent means what? Being male or female, getting the result, exam result being pass or fail, finally getting the result or pass or fail. It depends on gender. Whereas here, it doesn't depend on gender because both the places same the percentage. So that is known as chi-square test. So you do this chi-square test. If the chi-square value, observed and expected values are far away, then the chi-square value will be high. If the chi-square value is high, chi-square test distribution doesn't look like this. It looks like this. If the chi-square value is high, then the p-value will be less. That means observed and expected are far away. Observed and expected are far away. That means dependent. Observed is close to expected, then independent. So here in chi-square test, null hypothesis is independent. That means your observed values is equal to expected value. Observed means whatever we got it here in the result. Dependent is the alternative hypothesis. That means observed, whatever you have observed, whatever you got is not equal to whatever you are expected. Tell me, if this is the data that you have, when you do chi-square test, if this is your final data, are you going to see there is a dependency of gender on exam result, or gender and exam result are independent? What will you get as the result? Here,
There is dependency.
They are dependent.
Dependency. Will you get a very small chi-square value, or will you get a very large chi-square value?
It would be large and p
Why it
value
will be large? Because your
difference is there.
expected and your observed, there is a huge dependency, huge difference. That means when it is independent, you expect like this, but you got very, very different numbers. So that is why chi-square will be large. Once again, tell me, if the chi-square value is large, that means your expected and observed will be very, very different. In terms of testing of hypothesis, what will you test? Your, like, if the result is like this, your H0 is independent, your H1 is dependent. Are you going to accept the null hypothesis if this is the value? Are you going to reject the null hypothesis?
Reject.
Why reject? Because observed and expected. We are expecting 300 here, 300 here, 200 here, 200 here. But observed values are very, very different. That's why we reject the null hypothesis. You will get a very high chi-square value, higher chi-square value, very low p-value. That means we reject the null hypothesis. Then we will finally say this gender depends. The exam result depends on the gender. Do you agree? In this case, exam result, does it really depend on the gender?
Yes.
Yeah, in this particular example, I'm not talking about the general sense. I'm saying based on this data, exam result does depend on the gender. Okay.
Yes.
So let me ask you a question. If you go to bank market data on all the categorical variables, okay, I want to get this. This is known as contingency table. Perform this contingency table and tell me which variables are dependent, which variables are independent of the target. The target variable is customer purchasing an insurance or not purchasing an insurance. Now, does the job decide, or is there any relationship between customer purchasing an insurance versus this job variable, job type? Does it impact? Or the second variable is, let's say, education. Customer purchasing or not purchasing, is education independent of this or dependent on this? Using the chi-square, we want to do this test. Go ahead, do the chi-square test. Tell me which variable is independent, which variable is dependent. So go to the So ignore this IG for continuous target. Information gain we have discussed multiple times. So go to this chi-square test. So this is a visualization. Different ways of visualizations are there. You can show any visualization, but what really matters is how do you quantify it? Because visualization, people don't really get impressed whenever you are participating any of the assignments or something. Visualization, it seems that anybody can create this graph, but these kind of tests, let's say if you want to find out whether a categorical versus categorical. So here I'm creating between all the categorical variables. These are all the cross tabs. Customer education, customer buying the insurance or not, does it depend on education? Is it independent of education or dependent? Is it independent of housing loan or dependent? Is it independent of marital status or not? Is it independent of job type or not? Like that, we want to do the chi-square test. When we do the chi-square test, we will find the results. Let's do the chi-square test. When you are rejecting null hypothesis, what does that mean? When you are rejecting null hypothesis, let's say job type. So finally tell me variable by variable, job type. Customer buying or not buying, does it depend on job type or not? Simple question. Customer buying an insurance, target variable, does it depend on job type or it is independent? First tell me that answer. P-value is high, you accept the null hypothesis. When you accept the in chi-square test, what is the null hypothesis in all the chi-square tests? Let's say if you come back here, exam result and gender, what is the null hypothesis that we have? H naught, gender
distribution
and exam result are
same.
independent or dependent? What is the null? What is the null hypothesis here? Huh?
Independent.
Independent, isn't it? Because we are creating this table based on their independence, isn't it? When it is independent, then only you will get 300, 200, 300, 200, 60, 40, excluding whatever is the type of the variable. Okay. So if you go back to your code, you are accepting null hypothesis, job type and target variable. Are they independent or dependent? That is a question that I want to ask.
That is dependent.
So
because if you see the values, no are more and S are less.
correct. So do we decide based on the table values or do we do the testing?
We have to prove it. So we have to
Yes.
apply the
Testing. So you have done the chi-square test. You got the p-value. P-value is how much? 0.38, right? Are you going to accept the null hypothesis or reject the null hypothesis?
Accept it.
we have to reject because distribution should be same in the null hypothesis. But here we see the difference, right?
So you should not see the numbers, because if overall S is less, almost
Mhm.
everywhere S will be less only. Let me give you an example. Let us suppose in the same example, there are 1,000 students. People who have passed are 900. People who have failed are 100. Okay. Male are around 500. Female are around 500. Now look at this. In the same example, passed are 900, failed are 100. So look at this here, out of 500, 450, 50, 450, 50. Look at this. Does the table look similar to the table over here?
Yes.
Yeah. Now tell me, exam result, is it independent of gender or is it depending on gender?
Independent.
Independent.
Why independent? Because these are not same, right? Same thing. Look at this, but if you see here,
That's
90%, 10%,
Yeah.
90%, 10%. Yes or no? Since the
Yes.
overall number itself is lesser, that's why these numbers will be always less. Do you agree?
Yes, I understood.
Yeah. Whereas here, if you see, how do you finally see? Who will finally decide this? Chi-square test will decide it, isn't it? You do the chi-square test. You look at the p-value. If the p-value is less than 0.05, what do? You accept the null
Accept it.
hypothesis, right?
Mm.
What is the null hypothesis? So here p-value is 0.38. Okay. By the way, p-value less than 0.05 means what? You reject the null hypothesis, right? P-value less than 0.05 means far away. You reject the null hypothesis. Here p-value is 0.38. P-value is 0.38. You will accept the null hypothesis. As soon as I said p-value, what you should imagine? P-value and then 0.38. Close by or far away? 0.38 p-value. 38% is the p-value. Close by or far away?
Close
It's
by.
close by.
Close by should come into the picture. Close by means what? Accept or reject?
Accept.
Accept. What are you accepting here? Independence or dependence? What are you accepting?
Independent.
Yeah. So what are we saying? Job type. So tell me finally, job type. Is it independent of target
Independent.
variable or dependent? Think about it, all of you. Look at all these steps. You are accepting the null hypothesis. So does it matter? Job type.
No.
A
No.
customer
It's
buying or
independent.
not buying. Does it matter? Yes, these numbers are higher. These numbers are lower. Why? Because the whole population distribution is like that. Almost 90% here, 10%, 90, 10, 90, 10 like that. Okay. That's the reason. Or let's say 80, 20 kind of thing. Marital status and person buying or not buying. Does it impact? Marital status versus person buying or not buying. When you are accepting null
They are
hypothesis,
independent.
when you are accepting null hypothesis, what is null hypothesis in chi-square test? All of you participate. Tell me what is null hypothesis in chi-square test?
They
Independent.
are independent.
They are independent.
Independent, isn't it? Independent. X and Y are independent. Based on that only we are creating here, isn't it? We are following that assumption only. Why did we write 300, 200, 300, 200 here? Because if everything is independent, this is the expected table. Do you agree?
Yes.
Based on that only, our null hypothesis is independent. Alternative hypothesis is dependent. So that means accepting null means we are accepting their independence. Education, does it matter? A customer buying or not buying, does it depend on education?
Yes.
Why?
Independent.
Why do we say that?
Because
Because
it is alternative.
we are rejecting the null
Rejecting.
hypothesis. You are rejecting what you are rejecting. You are rejecting that they are independent. When you reject their independence, what you are accepting? You are rejecting that null hypothesis. All of you
Yes,
think
they are
about it.
independent.
So there is some dependency. What about this one? Same. This one is same variable, we ignore that, y versus y only. Housing loan, yes or no versus like that. So based on whether you accept or reject the null hypothesis, based on that, this is known as chi-square test of independence. It is used to test whether two categorical variables, whether they are independent or dependent. That you can give that by use. Usually you can create a pivot table. You can show using simple percentages also, you can explain, isn't it? Let's say out of male, around 20% have passed or 80% have failed. Out of female, around 100% have passed, 0% have failed. Overall pass percentage is 60, overall fail percentage is 40. There's a huge difference. So male and female, it does matter. Like that, you can convince somebody, isn't it? Just by showing pivot table and percentages also, you can convince somebody. Do you agree? But how do you prove it statistically? Using the chi-square test of independence. Is this chi-square test of independence the final inference? Is it clear? Accept null. What does that mean? What are we trying to tell finally? When I'm accepting null, I have found the chi-square
They are
test, I did
independent.
the x and y. So accept null means what? What am I accepting? They are independent. Why? Because everything starts from here. These are the exam result is independent of gender, then only this table is created, and we are comparing the real results with this table. That is why. Reject null. Reject null means what? X and y are independent, that we are rejecting it. That means we are accepting the fact that they are dependent. So out of all the tests that we do, test for mean, where we do the Z test, and the test for independence, chi-square test, these two are the kind of widely used important tests. Anyway, in regression, we use the test for beta I being 0 or not, where the variable xi, whose coefficient is beta I, is impactful or not, xi variable is impactful or not. That is also coming from the testing of hypothesis only. Finally, we do the judgment based on the final p value there. That is the whole concept of testing of hypothesis. Any final questions on this?